Okay, welcome to lecture 17 for ECE 203. Today we're going to talk about the frequency response of FIR, or finite impulse response filters. Okay, so another important way to characterize a filter is by its response to a sinusoidal input. We've seen a couple ways to characterize filters. Well, I guess really just one, and that's the impulse response, and that's how does the filter respond when we input a impulse signal, okay, a delta signal, a delta spike, right? And that was characterized by what we called the impulse response, denoted H of n. And then we showed that for a general input, if we just input the signal x of n, where that's just some general signal, into the same filter H, then the output we get is the convolution, right, between H of n and x of n. Right? So that impulse response gave us one way to characterize the filter and then calculate the output for any general input. So a third way, or a third thing we're going to look at, kind of a second way to characterize a filter, an FIR filter, is by looking at the frequency response. Okay? And the frequency response is just the response to the filter when we input a complex exponential signal. So that's written right here. If we just input a complex exponential at a digital frequency f hat, and we look at the output, then we get the frequency response of the system. So why is this interesting? Well, let's kind of take this apart. So I'm just, we can use this result, the general input result, and we can write the output when we input a sinusoidal, complex exponential input as follows. Right, this is just what's underlined in green here. That's just the convolution between the impulse response and the input e to the j 2 pi f hat n. And so why is that interesting? Well, note the following that I have written down below. We can really just expand this complex exponential, right? I can write that as e to the j 2 pi f hat n times e to the minus j 2 pi f hat k, right? And this term does not depend on k. And remember, that's inside the sum, so I can just factor that out. And that's exactly what I did down here. I've now factored out e to the j 2 pi f hat n. Right? The sum over k doesn't depend on that. And so why is that interesting? Well, that's just the input again. Right? So what is that telling us? If we input a complex exponential into a FIR filter, then what we get is kind of a scaled version of that input. Right? So we get the input signal back, and then that's multiplied now by this sum from k equals minus infinity to infinity of h of k, the impulse response, times e to the minus j 2 pi f hat k. And what's underlined here, note, right, does not depend on n. Okay, it only depends on f hat and h, right? So it depends on the filter, which is h, and then it depends on the particular frequency of the input complex exponential. All right. So again, let me try and state why that's interesting, why that's important. So when we input a complex exponential in general into an LTI system, here just think of an FIR filter, then the output we get is just another complex exponential at the same frequency, right? The same frequency f hat, and now it's just scaled by some number, right? And that number is given by this sum that's underlined here and denoted h of f. So we're going to call h of f hat the frequency response of the filter. And if that seems a little confusing, we're going to kind of break this apart, and we'll see this both in this lecture and in the next lecture. So this really sets in exactly what's happening here. Okay. So really, I kind of have written what was written on the last page just a little more explicitly here. Same idea, input complex exponential, right? This is our input signal x of n. and then the output we get ends up being x of n, right? That's the same thing we input. That's this what I just underlined is x of n, times some number h of f hat, or h of f hat is called the frequency response of the filter. And the reason I could do that is I could just factor this apart and then take the term that doesn't depend on k outside of the sum. And that was my original input signal. And that left me with this term, and that term does not depend on n. All right? Okay, so again, f hat is the frequency response of the filter h. Right? So in general, when we're describing a filter, we'll use the letter lowercase h or capital H, either one. And so an example now of what happens when we input a cosine signal, right? So we saw what happens when we input a complex exponential, but we can actually just now kind of use this same idea and use the fact that we know the filter is linear, so we can break this cosine up using Euler's identity, right? And that's all I've done on this second line. Just taken this a cosine 2 pi f hat n plus phi and now split it up using Euler's identity. So now we have something at a negative frequency f hat and a positive frequency f hat. Okay, so we have these two terms, and we know that the output of these, when these two terms added together go in, that should be the same as the output as if we pass each term in by itself, right? That was kind of the linearity property that we learned about. And if we do that, then what we see, of course, this first term, this is at a frequency of f hat. So all we have to do to get the output is multiply that input, that same input signal, by h of f hat, right? And likewise, for the negative frequency, the term with the negative frequency, all we have to do to get the output there is multiply that by h of minus f hat, right? Because that was at a frequency of f hat, of course, in units of cycles per sample. Okay, so we can see kind of now a rule for doing this. We could just put things back together using Euler's identity. And what happens when we input this cosine signal? Well, we really just get the magnitude of the frequency response at the frequency f hat, the frequency response h of f hat, and that gets multiplied by this cosine, and then we also have to add the phase change that the filter has kind of created at this particular frequency f hat, right? So this is interesting. We input a sinusoid at a frequency f hat to an LTI system. We get out another sinusoid that's at the same frequency, okay, but now it has amplitude depending on the absolute value or the magnitude of the frequency response of the filter, right? That's written there. And now the phase might have changed, right? You also have to add the effect of the phase of that filter at that particular frequency f hat. All right, so let's look at some examples of filters that we've seen before and see how see what their frequency response is. So let's take apart the 2-point moving average filter. We saw this before, and that's where we just take the output is equal to the half of the current input plus half of the previous input, right? And the impulse response of that is just 1/2 delta of n plus 1/2 delta of n minus 1. And we can, of course, plot that, right? And we just get two non-zero values at n equals 0 and n equals 1. So remember the formula for the frequency response, just the way we defined it on two slides ago, was capital H of f, this is the frequency response of the filter, is equal to the sum from k equals minus infinity to infinity of h of k e to the minus j 2 pi f hat k. Okay, that was just kind of our definition by seeing what happened when we input a complex exponential. Now, notice the limits on this sum, right, are from k equals minus infinity to infinity. But for the vast majority of values of k, right, h of k is 0, right? h of k is only non-zero here, right, when n equals 0 and 1. So there's really only two terms in this sum. So all I did in the next line is I just plugged in the definition of the impulse response, right? So right there, h of k equals 1/2 delta k plus 1/2 delta k plus 1, right? And so we're summing over all k. This signal here, right, in the parentheses, that's only non-zero for values k equals 0 and k equals 1. And so multiplying things out, we just end up with 1/2 times e to the minus j 2 pi f hat times 0, which is just 1. So that gives us this 1/2. And then for the term when k equals 1, then this second impulse is non-zero, and we just get 1/2 e to the minus j 2 pi f hat. All right. Now the next thing I want to do is I'm going to kind of factor out a couple of things. Okay. Maybe let me write an intermediate line here. We'll just write that. Well, we know that I could factor out of this 1/2. I could factor out e to the minus j pi f, right? And then I could multiply that by the quantity, say, e to the minus j, e to the plus j pi f, okay? Now, plus e to the minus j pi f, right? And so I think if we do this, I'm missing a constant of 1/2, write that here, divided by 2. Then we could multiply what I just wrote back out, and that should give us 1/2 plus e to the minus j 2 pi f hat. Right? Missing some f hats here. Hat, right? And then we can see this term in the middle, we could bring that 2 inside, and that's just cosine pi f. Okay? So now we've written the frequency response as just e to the minus j pi f hat times cosine of pi f hat. Why do we want to write it in this form? Why didn't we just leave it as the sum of those two individual terms? That was pretty simple, right? Well, this way we can see exactly what the magnitude is and what the phase is. It's totally transparent, right? If we take the magnitude of this h of f hat now, we take the absolute value of this, well, the absolute value of e to the j something times some other number, right? We know that we can just take the absolute value of that e to the minus j pi f, and that's always 1, right? So all we're left, if we look at the, write this here, h of f hat, if we look at the absolute value, right, we just get, we can write that as absolute value e to the minus j pi f hat times absolute value of cosine, right? And this first part, this is just 1, so that goes away. So let me erase that. And all we're left with is the absolute value of the cosine, right? So we get absolute value of cosine of pi f hat. Okay, and that's exactly what I'm plotting in this magnitude plot here, right? Just plotting over the range of digital frequencies of minus 1/2 to 1/2 cycles per sample, right? The absolute value of cosine of pi f. Make this a little more explicit. This is a pi, not an n. Okay? And so at a value of f hat equals 0, cosine takes on the value of 1. At a value f hat equals 1/2, cosine takes on the value of, then it's cosine then pi, cosine of pi over 2, which should just be 0. Right? So you can see the absolute value goes to 0 at both of kind of the endpoints. So in words, this would be called a what? This would be a low-pass filter. And why is it called a low-pass filter? Well, because it passes low-frequency components, meaning if I input a sinusoid, we can think of this as follows. If I input a sinusoid with the digital frequency that's low, say at this frequency, I just drew this arrow, right? Then that just gets multiplied by about this value, which is really close to 1. So these low frequency components go through. But conversely, if I try and pass a sinusoid through the system, try and filter a sinusoid that's at a higher frequency, say out here, then that gets multiplied by this value. So that gets almost knocked down to 0. All right, so again, what does this plot tell us? This tells us how, when we input sinusoids, how those sinusoids get scaled when they come out of the LTI filter. All right. And then, of course, we can also plot the phase. Plot the phase of this, and the phase just comes from what's written there, right? It's just a plot of minus pi f, okay? Right? So remember, if we have e to the j theta, the phase is just theta. Okay? So that's all I'm plotting here. That's the phase of the filter. So if we input a sinusoid, we can also use this phase plot to understand how the phase is affected by the filter. Okay, let's look at another example, and that's the digital differentiator. Okay, this is a filter that we've seen before, and it has the impulse response h of n equals delta of n minus delta of n minus 1, right? So it just takes two adjacent samples, right, and subtracts them. Okay, so that's plotted right here, right? For the n equals 0, it takes on the value 1, and for n equals 1, it takes on the value minus 1. And so we just look at the definition of the frequency response of the filter, and we write that out. Okay, this is a sum from k equals minus infinity to infinity of h of k e to the minus j 2 pi f hat k. Okay, and then I would just plug in. All I'm doing here is plugging in the definition of the impulse response, and notice that that's only non-zero for the values k equals 0 and k equals 1. So when k equals 0, we end up with this impulse, this delta, times e to the j 2 pi f hat times 0. So that just gives us a 1, right? And then the second term is when k equals plus 1. Okay? So when k equals plus 1, this delta is being non-zero, and we're left with a minus 1, but now times a complex exponential evaluated when k equals minus 1. So it's the total frequency response is 1 minus e to the minus j 2 pi f hat. And we're going to play the exact same trick that we did before. Okay, and what's that? Well, it's just factoring out, let me put a box around this. This is a totally valid expression for the frequency response of this filter. But in order to see kind of the magnitude and the phase, we're going to play the same game that we did before. And that's, first I'll factor out an e to the minus j pi f hat, right? And note, of course, that when I multiply e to the minus j pi f hat times e to the plus j pi f hat, that just gives me 1. And then again, I multiply e to the minus j pi f hat times minus e to the minus j pi f hat. I get minus e to the minus j 2 pi f hat. All right, so I know that was a mouthful, but it's pretty easy to check that these two expressions are equal. Okay, so then the next thing I'm going to do is now I'm just going to notice that I can write this guy in terms of the sign, right? Remember Euler's identity, e to the j, let's just write it like this, Euler's inverse identity, sine of theta equals e to the j theta minus e to the minus j theta, right, divided by 2j. Okay, so you can convince yourself that this whole thing can just be written as 2j times sine of pi f hat. That's exactly what I did. And then, again, I'm going to rewrite j. I'm going to rewrite that as e to the j pi over 2. Trying to write here. So j, it's equal to e to the j pi over 2. Okay. And then now I'm just combining these exponents. I still have the 2 here, right? Just make sure everything's accounted for. The sine pi f is there. And then I also need this, I'm factoring e to the j pi over 2 and multiplying that by e to the minus j pi f hat, and that gives me this expression here. Okay. So if I look at the magnitude of that, the absolute value of that h of f, all I get is really just the absolute value of sine, right? So 2 times the absolute value of sine pi f hat, right? You write that down here. H of f hat, the absolute value, equals 2 times the absolute value of sine pi f hat. The reason that is just because this phase term doesn't contribute to the magnitude, right? The absolute value of e to the j, anything, is always 1, right? So I'm plotting that 2 times the absolute value of sine pi f hat here, right? That's all this plot is. And that tells us again now how a sinusoid at a different frequency would be affected by this filter, the amplitude of that sinusoid. All right, so if it were think of this as if it were a low frequency sinusoid, maybe somewhere down here, it would be really attenuated, meaning it would be really knocked down close to 0. The amplitude or the gain that it would see would be pretty small. But likewise, if we tried to pass a kind of a high frequency digital sinusoid through this filter, then the gain it would see would be about 2, right? So this is, this we would call a high pass filter. All right? It's a high pass filter because high frequency sinusoidal inputs get passed through. All right, so the last thing here is the plot of the phase of this signal. And one thing you can do is just compute this in MATLAB and make a plot like this. But you can also kind of go through this by hand like we did on the last slide. It's a little more complicated here. And really, if we note that h of f hat, that's just a complex number, right? And so we want to write that in the form r e to the j theta. Okay, that's kind of the whole goal here, where both r and theta, they're also functions of f hat. But and so we could write that as r of f hat e to the j theta of f hat, right? And we're looking for r to be some positive number. Okay, that's the magnitude of this signal. So r is the magnitude. We already plotted that over here. But theta is the phase. So in order to find the phase, well, in this case, it's a little more complicated. We'd see when f hat is positive, the sine function takes on a positive value. So in that case, theta is just given by what I'm underlining right there, pi times quantity 1/2 minus f hat. And sure enough, that's a plot of this line here, right? But when sine of f hat is negative, right, which happens when f hat is less than 0, then we somehow have to adjust the phase, right? We have to adjust our definition of r so that it's still positive. And the way we do that is basically by adding another factor of e to the minus j pi, right? Because e to the minus j pi is just minus 1. Okay, so if you didn't follow all that, I guess it's not too important because we're mostly going to focus on how magnitude affects these sinusoidal inputs and not how the phase is changed. So I want to do very briefly one more example, and that's a slightly more complicated one. It's kind of a one now where we take the impulse response to have non-zero values for n equals 0 and n equals 3. Right? That's just given by that expression there. Again, do the same thing, just look at the frequency response definition, which we saw 3 slides ago now, and then we just start plugging in. The first thing I would do is notice that k, even though the sum is from minus infinity to infinity, h of k is only non-zero for n equals 0 and n equals 3. Okay? So I'm going to plug in now, again, this first term comes from, well, when k equals 0, we have 1 times e to the minus j 2 pi f hat 0, that's just 1. Likewise, when k equals 3, then we end up with 1 times e to the minus j 2 pi f hat times 3, which gives me this 6 pi. Right? And again, now factor out, same trick, factor out this term, and then realize we're left, using Euler's inverse identity, what we're left with is the following expression. Right? We have, and this is our magnitude term, and this is our phase term. Right? So if we look at the absolute value of h of f, we just get 2 times cosine of quantity 3 pi f hat, and the phase, the angle, is just minus 3 pi f hat. We use this symbol to denote the angle, or the phase. Right? And I can plot both of those. It's not too tough to plot either one of those. Just by plugging in some values and looking at what we know the period of this sinusoid would be. Okay, that's all we'll do for today.